Sophie Germain's secret. Imagine it's the early 1800s. You are Carl Friedrich Gauss, the undisputed prince of mathematicians. A mind so vast that your contemporaries struggle to even keep pace. You live and breathe the elegant, unyielding logic of numbers. One day, a letter arrives. It's from a correspondent in Paris, a man who calls himself Monsieur Antoine-Auguste LeBlanc. You've been exchanging letters with him for some time now, and with each one, your admiration grows. This Monsieur LeBlanc is no mere student. He is a peer. His insights into number theory, your own specialized domain, are not just brilliant, they are groundbreaking. He sends you elegant proofs, new avenues of thought, and demonstrates a profound understanding of your most complex work. You write back to him, filled with the rare and exhilarating joy of finding a true intellectual equal, praising his superior genius. You are convinced that this man, this Monsieur LeBlanc, is one of the most promising mathematical minds in all of Europe. You have no reason to think otherwise. The name is French, the handwriting is firm, the logic is impeccable. It all fits. But you would be completely, utterly, and magnificently wrong. Because Monsieur LeBlanc does not exist. He is a phantom, a carefully constructed fiction, a name on a page designed to open a door that, by law and by custom, was bolted shut. The mind you have been corresponding with, the genius you so deeply admire, does not belong to a man at all. It belongs to a young woman living in Paris, a woman who has never attended a university, has never had a formal tutor, and is barred from the very academies and scientific societies where knowledge is shared. Her name is Sophie Germain, and she has just pulled off one of the most audacious and brilliant deceptions in the history of science. This wasn't a prank or a simple game. It was a radical act of intellectual survival. Sophie Germain, cloaked in shadow, writing at a desk, was fighting a war on two fronts. The first was against the abstract, complex problems of mathematics and physics. The second, more insidious war was against a society that had already decided who she was and what she was capable of based entirely on her gender. In late 18th and early 19th century France, the world of higher learning was a fortress of masculinity. The great institutions, the École Polytechnique, the French Academy of Sciences, were exclusively male domains. The prevailing belief, supported by philosophers and physicians alike, was that the female mind was simply not built for the rigors of abstract thought. It was considered too emotional, too delicate, too preoccupied with domestic matters to grasp the cold, hard truths of calculus or number theory. For a woman to even express an interest in such subjects was seen as eccentric at best and unnatural or even dangerous at worst. It was a violation of the social order. So, what was a burgeoning genius to do? Sophie Germain understood the rules of the game, and she chose not to play. Instead, she invented a new player. She discovered that a former student of the famed École Polytechnique, Monsieur Antoine-Auguste LeBlanc, had left Paris. His name remained on the student rolls, and lecture notes were still being produced for him. In a stroke of daring brilliance, Sophie assumed his identity. She began obtaining the lecture notes from professors like the great Joseph Louis Lagrange. She would study them, complete the assignments, and then, signing them as LeBlanc, she would submit her work. Her solutions were so remarkable, so full of originality, that they quickly caught the attention of Lagrange himself. He was astounded by the quality of this student's work and requested a meeting. The ruse was up. Sophie was forced to reveal her true identity. But instead of being met with anger or dismissal, Lagrange was astonished and, to his credit, deeply impressed. He became one of her first and most important mentors, opening doors that would have otherwise remained sealed forever. But corresponding with Lagrange was one thing. Writing to the formidable Gauss in Germany was another level of audacity entirely. She knew he would never take correspondence from a woman seriously. The name LeBlanc was her shield and her key. It allowed her ideas to be judged on their merit alone, stripped of societal prejudice. It was a test. Could her mathematics, pure and unadorned, stand shoulder to shoulder with the greatest practitioner alive? The answer, as Gauss's enthusiastic replies proved, was a resounding yes. A side-by-side of two letters, one signed LeBlanc, the other Germain, represented more than just a change in name. They represented a rebellion. This secret identity was the central defining act of her early career, a testament to her unwavering determination. She wasn't just solving for X, she was solving for her own existence in a world that sought to render her invisible. She built a man out of ink and paper so that she, the real person behind the pseudonym, could finally participate in the great scientific conversation of her time. It was a strategy born of desperation, but carried out with such genius that it would change her life and the course of science forever. And it all started in the quiet solitude of her father's library, amidst the chaos of a revolution that was reshaping the world outside her window. Self-taught mathematician. To understand the mind that conceived of Monsieur LeBlanc, we have to travel back to the very heart of the French Revolution. It's 1789. Paris is a city convulsing with change, a tinderbox of radical ideas and political violence. The Bastille has fallen, and the reign of terror is on the horizon. For most, it was a time of uncertainty and fear. But for a 13-year-old girl named Sophie Germain, the chaos outside was a strange kind of opportunity. Confined to her home for her own safety, the daughter of a wealthy silk merchant, she found her entire world condensed into the four walls of her father's expansive library. It was here, surrounded by leather-bound books and the quiet hum of intellectual history, that her own revolution began. She wasn't reading novels or poetry, she was drawn to the books on mathematics. Her defining moment, the spark that lit the fire, came from reading an account of the life of the ancient Greek mathematician Archimedes. She was captivated by the story of his death. As the story goes, when Roman soldiers stormed the city of Syracuse, they found Archimedes completely absorbed in a geometric problem, drawing circles in the sand. He was so lost in his work that he famously told the soldier, "Do not disturb my circles," and was struck down. Sophie was thunderstruck. What kind of subject, she wondered, could hold such power over a person's mind that it could make them oblivious to chaos and even death? This, she decided, was the most beautiful and powerful pursuit in the world. This was what she wanted to do. She began to devour every mathematical text she could find in her father's collection. However, her newfound passion was met not with encouragement, but with fierce opposition from her own family. Her parents, though educated and progressive for their time, were horrified. This was not a suitable interest for a young woman of her social standing. It was unfeminine. It was unhealthy. They were convinced that the intense intellectual effort would damage her delicate constitution and her mental well-being. So, they began a campaign to stop her. Her parents, taking away her candles and fire, was not an act of cruelty in their minds, but one of protection. They confiscated her candles so she couldn't read at night. They took away her warm clothes and let the fire in her room go out, hoping the physical discomfort would drive her back to bed and away from her books. But they had fundamentally underestimated their daughter's resolve. Sophie Germain was not one to be deterred. She became a creature of defiance and ingenuity. She would save her candle stubs, hiding them away to be used in the dead of night. When the fire went out, she would pile quilts on her bed, wrapping herself in a cocoon of blankets, and continue to study, sometimes waking in the morning to find the ink in her inkwell had frozen solid.
This image of a young girl shivering under a mountain of blankets, scribbling equations by the faint light of a smuggled candle, is the very essence of her character. It is a portrait of pure, unadulterated intellectual passion refusing to be extinguished. Her determination was so absolute that her parents, seeing they could not stop her, eventually relented. They had lost the battle. Sophie had won her right to study. But a new, more formidable obstacle immediately presented itself. The most important cutting-edge works in mathematics and physics, the writings of giants like Isaac Newton and Leonhard Euler, were not written in French. They were written in Latin and Greek. For most people, this would have been an insurmountable barrier. For Sophie Germain, it was just another problem to be solved. With no formal instruction, she painstakingly taught herself both classical languages. A page of Newton's Principia in Latin with Germain's handwritten French notes in the margin would have been a common sight in her study. She wasn't just translating the words, she was wrestling with the very fabric of calculus and celestial mechanics alone. Think about the profound isolation of this period. She had no teachers to guide her, no classmates to debate with, no mentors to ask for help when she was stuck. Her entire education was a silent conversation between herself and the greatest minds in history, mediated through the pages of their books. She was building a world-class mathematical education from scratch, driven by nothing more than her own curiosity and iron will. She was a self-made scholar in the truest sense of the word. This intense period of solitary study forged her mind into a powerful and original instrument. She wasn't just learning what was already known, she was developing her own unique way of thinking, her own approaches to problem-solving. But knowledge, especially in a field like mathematics, cannot exist in a vacuum. To truly grow, to test her ideas and push the boundaries of what was known, she needed to emerge from the library. She needed to engage with the living, breathing mathematical community. And that community, as she knew all too well, had a "No Women Allowed" sign on the door. Her clandestine, self-directed education had given her the knowledge, but now she needed a key to unlock that door. That key, she realized, would have to be a man. And so, Monsieur LeBlanc was born, not just from a need to hide, but from a deep, burning desire to connect, to contribute, and to finally test her mettle against the greatest of them all.
Block 3. Gauss's correspondence with her secret identity as Monsieur LeBlanc established, Sophie Germain set her sights on the highest peak in the mathematical world, Carl Friedrich Gauss. This was no small ambition. Gauss was a living legend, a prodigy who had made fundamental contributions to a dozen fields before the age of 30. His 1801 masterpiece, Sorcalo de Elementis, had single-handedly revolutionized number theory, the study of the properties of integers. It was a work of such density and brilliance that even many professional mathematicians struggled to comprehend it. For Sophie, it was a revelation. She dove into its pages, and unlike many of her contemporaries, she didn't just understand it, she began to build upon it. She started writing to Gauss in 1804 under her now trusted pseudonym. She knew that sending a letter as Sophie Germain would likely result in it being politely ignored or, worse, discarded as the ramblings of a dilettante. But a letter from Monsieur LeBlanc, a promising young scholar from Paris, would surely command his attention. She was right. Her letters were not those of a student asking for help. They were letters from a peer. She discussed some of the most difficult concepts in Gauss's book, offering her own proofs and observations. Her primary focus was on a problem that had haunted mathematicians for centuries, Fermat's last theorem. This famous conjecture stated that there are no three positive integers, a, b, and c, that can satisfy the equation an plus bn equals cn for any integer value of n greater than 2. It was a deceptively simple problem that had resisted all attempts at a solution.
Sophie didn't solve it, but she developed a powerful new line of attack. She devised a theorem now known as Sophie Germain's theorem, which provided a major step towards a proof for a huge class of numbers. It was a piece of work so original and profound that it stunned its recipient. Gauss was captivated. He had found a kindred spirit. In his replies to LeBlanc, his admiration is palpable. He wrote, "I am delighted that the arithmetic has found in you so able a friend." He praised LeBlanc's ardor and sagacity and encouraged him to continue his work, completely unaware that the brilliant mind he was mentoring belonged to a woman who was defying every convention of her society to even hold a pen. This secret correspondence continued for 3 years, a vibrant exchange of pure mathematical thought, unburdened by prejudice. For Sophie, it must have been an intoxicating experience. She was, for the first time, being seen for the pure power of her intellect. The validation from the great Gauss himself was proof that her solitary studies had not been in vain. She truly belonged in this world. But the real world, a world of politics and war, was about to intrude on their intellectual sanctuary. In 1806, Napoleon's armies marched across Europe, invading Prussia. The city of Brunswick, where Gauss lived and worked, was now in the path of the French forces. Sophie was filled with a terrible sense of dread. She remembered the story of Archimedes, killed by a soldier while lost in thought. She couldn't bear the idea of the same fate befalling her hero and correspondent, Carl Friedrich Gauss. She had to do something. Using her family's connections, her father now had friends in high places, she reached out to a French general who was a family friend, Pernetti, who was the commander of the French forces in the area. She begged him to ensure Gauss's safety. General Pernetti, moved by her passion, sent a dispatch to Gauss letting him know that he was safe, and mentioned that he was doing so at the request of a Mademoiselle Sophie Germain. Imagine Gauss's confusion. A French commander ensures his safety, attributing it to a woman he has never heard of. Sophie Germain? Who was she? The pieces didn't add up. The general had let the cat out of the bag, and Sophie knew her time as Monsieur LeBlanc was over. With a mix of trepidation and resolve, she sat down and wrote another letter to Gauss. This time, she signed her own name. She confessed everything, the pseudonym, her gender, her reasons for the deception. She had laid her genius bare, and now she could only wait for the verdict from the highest judge she knew. The response that came back is one of the most remarkable and moving documents in the history of science. Gauss was not angry. He was not dismissive. He was utterly, profoundly amazed. He wrote to her, "But how to describe to you my admiration and astonishment at seeing my esteemed correspondent Monsieur LeBlanc metamorphose himself into this illustrious personage? When a person of the sex, which, according to our customs and prejudices, must encounter infinitely more difficult than men to familiarize herself with these thorny researches, succeeds nevertheless in surmounting these obstacles and penetrating the most obscure parts of them, then without doubt she must have the noblest courage, extraordinary talent, and superior genius." Gauss's letter of praise to Sophie was more than just a compliment. It was a coronation. The Prince of Mathematicians had not only accepted her, he had celebrated her. He saw her not as a woman who was good at math for a woman, but as a genius, period. He understood the courage her deception had required and admired her all the more for it. This moment was the ultimate vindication. Her secret was out, but instead of ridicule, she had found acceptance and admiration at the highest possible level. This newfound confidence would propel her out of the abstract world of number theory and into her next great challenge, a very public and very physical battle with the physics of vibrating plates.
Block 4. Elasticity Theory Pioneer. Fresh from the profound validation of Carl Friedrich Gauss, Sophie Germain was emboldened to step out from the shadows of pure mathematics and into the tangible, messy world of experimental physics. The timing was perfect. A new scientific puzzle had just captured the imagination of Paris. A German physicist named Ernst Chladni had been touring Europe performing a mesmerizing demonstration. He would take a thin metal or glass plate, sprinkle it with fine sand, and then draw a violin bow along its edge. As the plate vibrated, the sand would magically arrange itself into stunningly intricate and beautiful geometric patterns. These became known as Chladni figures, sand forming beautiful patterns on a vibrating plate. The effect was captivating, but no one could explain it. There was no mathematical theory that could predict or account for why a certain frequency produced a certain pattern. It was a mystery, and the prestigious French Academy of Sciences wanted it solved. In 1809, they announced a grand prize competition, the challenge to develop a mathematical theory that could explain the vibration of elastic surfaces. This was a problem of immense difficulty. Even the great Lagrange, who had reviewed her earlier work, declared that the mathematics required to solve it were likely not yet invented. It was a challenge so daunting that for 2 years, not a single mathematician in Europe submitted an entry. But Sophie Germain, working in isolation, decided to take it on. This was a radical departure for her. Her work with Gauss on number theory was private, abstract, a conversation between two minds. This was public, applied, and competitive. It was a direct attempt to storm the gates of the scientific establishment. In 1811, just before the deadline, a single entry was submitted. It was hers. The judges, a committee of the most eminent scientists in France, including Lagrange, Legendre, and Laplace, were intrigued. The paper showed a deep understanding of the problem and a brilliant, innovative approach. However, it also contained mathematical errors. Citing these flaws, they denied her the prize but extended the competition for another 2 years, implicitly encouraging the anonymous author to try again. Sophie was undeterred. She refined her work, corrected her derivations, and in 1813 she submitted a second entry. Once again, it was the only one. And once again, it was rejected. While her new equation was an improvement, the judges were still not satisfied with its rigor. It was during this period that she faced the full, crushing weight of institutional sexism. As a woman, she was not permitted to attend the sessions of the Academy. She couldn't be present to hear the judges' critiques of her work, to defend her methods, or to engage in the informal discussions where so much scientific progress happens. She was fighting with one hand tied behind her back, communicating through intermediaries and trying to guess the exact nature of the judges' objections from second-hand reports. Furthermore, she had a powerful rival on the judging committee itself, Simeon Denis Poisson. Poisson was a brilliant mathematician in his own right, and he was also working on the problem of elasticity. He was publicly dismissive of Germain's work, and there is strong evidence to suggest that he borrowed some of her key ideas without giving her credit, refining them with his superior formal training and presenting them as his own. It was a classic case of a powerful insider co-opting the work of a marginalized outsider. The Academy extended the competition one more time. Exhausted and frustrated, but refusing to give up, Sophie Germain went back to work. She spent the next 2 years revising, strengthening, and perfecting her theory. In 1816, she submitted her third and final entry. This time, she won. The judges, while still noting some shortcomings, could no longer deny the fundamental brilliance and importance of her work. Sophie Germain's name announced as the winner at the French Academy made her the first woman in history to win a prize from this august institution. It was a monumental achievement, a crack in the centuries-old wall of exclusion. However, the victory was bittersweet. The official report on her work was lukewarm, and she felt that her contribution was being deliberately downplayed by rivals like Poisson. Feeling that she had not been given the respect she deserved, she made a bold statement. She refused to attend the public award ceremony. She had proven she could beat them at their own game, but she would not celebrate with an institution that had made the game so fundamentally unfair.
Despite the politics, the impact of her work was undeniable. The equation she derived, while later improved upon, was the foundational stone upon which the entire modern mathematical theory of elasticity was built. Every time an engineer designs a skyscraper to withstand an earthquake or a bridge to handle the stress of traffic, they are using principles that trace their lineage directly back to Sophie Germain's prize-winning paper. She had taken a parlor trick with sand on a plate and turned it into the language of modern structural engineering, a legacy that would far outlive the prejudices of the men who judged her.
Block 5. Unsung science hero Sophie Germain's victory in the Paris Academy's competition should have been her coronation. It should have been the moment that the doors to the scientific establishment were thrown open, welcoming her as a peer. She had proven her genius not once, but twice, in two of the most difficult fields imaginable: the abstract purity of number theory and the applied complexity of elasticity theory. She had corresponded with Gauss as an equal and solved a problem that had stumped the greatest minds in France. By any objective measure, she had earned her place. And yet, that place was never granted. Despite her monumental achievements, Sophie Germain was never offered a paid position at a university. She was never elected to the French Academy of Sciences. For her entire life, she remained an outsider, an amateur in the eyes of the formal institutions of science, forced to work on the fringes of a world she had done so much to advance. This is the central, lingering tragedy of her story. We can only speculate what more she could have accomplished with the resources her male colleagues took for granted. Access to libraries, the stimulation of daily collaboration with peers, the financial security of a professorship, and most importantly, the simple, profound power of being recognized. How many more theorems lay undiscovered in her mind, waiting for the right conversation to bring them to light? It's a question that haunts her legacy. Her greatest champion, Carl Friedrich Gauss, certainly understood her value. In the final years of her life, he lamented the fact that she had never received the formal recognition she so richly deserved. He decided to use his immense influence to right this wrong. In 1830, he wrote to the faculty at the prestigious University of Göttingen in Germany, persuading them to award Sophie Germain an honorary doctorate degree. This was an almost unheard of honor for a woman at the time. It was to be the ultimate acknowledgement of her life's work from the world's most respected scientific institution, championed by the Prince of Mathematicians himself. The university agreed. The degree was approved. But in a final, cruel twist of fate, the news never reached her. The honorary doctorate certificate, unawarded, became a symbol of a recognition that came just moments too late. Sophie Germain died in 1831 at the age of 55, after a long and painful battle with breast cancer, before the university could officially confer the honor. The world had finally decided she was worthy, but she was no longer there to hear it. Even in death, the system sought to erase her identity. The official death certificate did not list her as a doctor or a masanda. Instead, it used the term a property holder or person of independent means. It was a final, bureaucratic dismissal of her entire life's passion and contribution, reducing her to her economic status, the one role society was comfortable with her occupying. But history's judgment is more enduring than that of any single institution or clerk. Her work lived on, becoming foundational to fields she helped create. Her theorem on Fermat's last theorem, often called Sophie Germain's theorem, was a critical tool used by mathematicians for over 150 years in their quest for a final proof. The Sophie Germain primes that grew out of this work are now essential in modern cryptography and computer science.
And, of course, her elasticity theory underpins the very structures of our modern world, from the Eiffel Tower, which was built using the principles she pioneered, to the airplanes that fly overhead. Sophie Germain's story is more than just a biography of a brilliant mathematician. It is a powerful and at times infuriating testament to the resilience of the human intellect against the friction of prejudice. She was a genius who had to invent a man just to be heard. She was a pioneer who had to fight for every scrap of recognition. Her life forces us to look into the shadows of history and ask a vital question. How many more? How many other brilliant minds were silenced, sidelined, or forgotten simply because they were born the wrong gender, in the wrong place, or at the wrong time? Sophie Germain's legacy is a challenge to us all, to recognize that genius knows no gender, and that the most profound discoveries often come from those who have the courage to defy the world in order to explain it. Her voice, once hidden behind a man's name, now echoes through history, a powerful and inspiring reminder of a mind that simply would not be denied.